Okay, the self-ionization of water and pH. So it's also called auto-ionization of water. Write the equation showing the auto-ionization of water. Well, two waters can come together and form, one gives up an H+, the other accepts it. And that is the deal. Now, so write the ion product expression for Kw. Now, the Kw is going to be the concentration of the products raised to their coefficients. If they're aqueous. On the other side, they're just liquids, so that's really it. Looks like I was going to write something below, but there's nothing to write below because these are both liquids, so they don't play a part. And this concentration at 25 degrees Celsius, or this expression is going to always be 1.0 times 10 to the minus 14. So if we at 25 degrees Celsius, since the number of H3O plus and OH minus are going to be the same, because it's 1 to 1, then it'd be, we could put in X as the unknown. And what we'd find at 25 degrees Celsius in pure water, the concentration of H3O plus is equal to the concentration of OH minus, and that is 1.0 times 10 to the minus 7 molar. So there's always 10 millionth of a molar of H3O plus and OH minus present in any pure water at 25 degrees Celsius. Can't have anything else in it. Now determine the concentration of H3O plus when the concentration of OH minus is 1.88 times 10 to the minus 3. Now we've just found this expression, the Kw expression. Now it's a Kc expression, but because it's for water we give it a special label of Kw. I'm going to put a third significant figure there. Now this holds no matter what we have. If it's pure water, then it's very simple. These are each 10 to the minus 7 molar. But if you put any acid or base in there, it's going to adjust these species. So we've added in 1.88 times 10 to the minus 3 molar OH minus. That means that we're going to have a drop in H3O plus so that the product will still equal this. So that's its purpose of having this expression, because it will tell us if we know the one concentration, we can always find the other. So let's do it out here. Concentration of OH minus. And that came out to be 0 for some reason. And this is 5.32 times 10 to the minus 12 molar. So you can see that it's dropped from 10 to the minus 7 for pure water down to 10 to the minus 12, and that's because we've added in this base. The base gobbled up a lot of the H3O plus in the process of going into solution. And that OH minus could have come from anything: sodium hydroxide, potassium hydroxide, ammonia, whatever it took to get to that concentration. So right now we're just interested in working with this equation rather than where all these concentrations came from. Determine the concentration of OH minus when the concentration of H3O plus is 10.5 molar. Okay, so we have this expression again. It's going to be our friend, so you should know this one. And then OH minus, if we rearrange, and I skipped a step last time. I think it's not too bad to do that, but I'm going to put everything in this time. And remember that we get rid of the units of measure. As long as we're in molars, we get rid of the units of measure. And this is 9.52 times 10 to the minus 16 molar. And then once we've done the calculation, we put the units back in. So as long as we're in molars for what we know, this is going to have no units of measure, and then we go back. Once we have our number, we convert back to molarity. Calculate the concentrations of hydronium ion, that's H3O plus, you should know that, and OH minus is hydroxide ion, in 1.5 1.53 molar strontium hydroxide solution. This is a strong base. That means that it will dissociate completely. So we can do our initial change equilibrium. This is 1.53 molar, 0, 0, minus 1.53, plus 1.53. Now, the big thing here is there's a 2, so that's going to become, was it 2.06 molar. That seems right. Oh, 3 point, sorry. Thought there was something wrong there. So we're going to add 3.56. It's doubled. We've doubled the amount, and then this is 0. All the base gets used up. It's a strong base. That's what happens. We get 1.53 molar of strontium ion. In this case, we don't really care about that. It's important as a counter ion, but it doesn't help us with the calculation. And then we'll have 3.06 molar of the hydroxide ion. So now we know what our hydroxide ion is. We want to know the constant. So that's our one answer. And then the hydronium ion is going to be 1.00 times 10 to the minus 14 over 3.06. Oops. We should expect it to be a smaller number by about 3 times. And so that's what we find. It looks good. And I just say that because sometimes people will flip these, and you should expect in the calculator, and they end up with something that's a fairly large number, or maybe a very large number, and that's how you should always be looking to make sure that your answer makes sense once you're done. Okay, calculate the concentrations of hydronium ion and hydroxide ion concentration in 3.55 molar HCl. Now the last one I did that ice table. This one we know that it breaks up into H+. Actually, let's do it properly. For us, we are going to have the water as part of the equation. Now I could do out the ice table, but we know that 3.55 molar HCl breaks up completely, turns completely into 3.55 molar H3O+ and 3.55 molar Cl-. So we can go through the whole thing, but you should know, since it's a strong acid and it's monoprotic, that we just the H3O+ concentration is going to be the same as the other one here. And you can see up here that we know the concentration of the base, but there's 2 OH minuses, so our final concentration of OH minus is twice that. If this had been sodium hydroxide, our OH minus concentration would have been the same. So seeing this stuff, you know, if you have to do out the ice table, that's fine, but you should be able to do this fairly quickly. These types of problems, because they're not weak acid or weak base problems where we'll see that next, where they can get very involved. These ones, if you just work with this enough, you'll start to see that you can make some quick calculations without using your calculator and be done a lot quicker. Okay, so that's our OH minus concentration, and our H3O+ concentration, though I didn't write it down directly, is this. So these are our two answers. What is a pH of 0.2 molar HBr? HBr is a strong acid, so we know that we're going to have 0.2 molar H3O+. So our concentration of H3O+, since it's a monoprotic strong acid, is going to be the same concentration. So pH is negative log of the concentration of H3O+, so it's the negative log base 10 of 0.2. So 0.2 log, so our pH is going to be 0.699. That's very low pH. It should be, because it is a strong acid, so we should expect that the pH should be less than 7, and since it's a fairly high concentration, it should be a very much lower than pH 7. We also know that pH plus pOH is equal to 14, and so our pOH is going to be 14 minus 0.699, and this is 13 0.3. We go out to 3 decimal places, so we can actually go out there. That 14 is exact. And so you should be able to, now we have H3O plus, we have OH minus, and we can convert between those. We have pH and POH, should be able to convert between those, and we know we can convert between these two as well. And POH is equal to the negative log of OH minus. So that allows us to do this conversion. And let me just, we'll go to this last problem. Let me just write it down here. Let's write all of the equations that we have. We have H3O plus, am I in there? Yeah. Times OH minus is equal to 1.00 times 10 to the minus 14. pH plus POH is equal to 14. pH is equal to negative log of the concentration of hydronium ion. POH is equal to the negative log of the concentration of hydroxide ion. The concentration of H3O plus is also equal to 10 to the minus pH, and so going the other route, the concentration of OH minus is equal to 10 to the minus POH. So we have 6 different equations here. I don't think I'm missing anything. I think that's everybody, that allow us to convert back and forth. So on the exam, you'll have, because this works just so well, it'll be something very similar to this. I have 4 different solutions, and I give you one I tell you either pH, POH, H3O plus, or OH minus for each solution. And then this means acidic, basic, or neutral. Just ran out of room. So I'm going to move this over. We don't need to see the solution numbers there. So then with one of these terms, you can fill in the rest of them. Well, first, pH is less than 7, so this has to be acidic. And then POH is going to be 14. I'm just going to do it quickly, but I'll be saying it using this equation. We have 14 minus 3.46, so this should be 10.54. The concentration of H3O plus is going to be 10 to the minus, where is it here? 10 to the minus 3.46. So it comes out to be 3.47 times 10 to the minus 4 molar. Big thing is to have units of measure here. And then, so 3.5, just double check. And then the OH minus is going to be 10 to the minus POH, so 10 to the minus 10.54, so this comes up to be 2.88 times 10 to the minus 11. Could have also found it using the original equation. So most of the time there's more than one way to reach the answer. And then to check to make sure you're right, multiply these two together. They should come up to be 10 to the minus 14, or very close to it. We rounded, so we should expect to be off slightly. And I get 9.99 times 10 to the minus 15, which would round to 1 times 10 to the minus 14. These two together must add up to 14, and they do. So for here we have pH, we have 15. The only way to get this down to 14 is to make this negative 1. pHs can be negative. That just means that it's extraordinarily acidic. pH of 0 means that you have a 1 molar solution. pH of negative 1 means you have a concentration of 10 molar H3O plus, which is easy enough to do. 10 molar HCl is readily available. 12 molar HCl is available. So for H3O plus, let me actually do this one out carefully. H3O plus is going to be 10 to the minus pH, and for this one it's going to be 10 to the minus 1, so it's going to be 10 molar. And then the concentration of OH minus will be 10 to the minus 14 divided by 10. So we should expect it to be 1.00 times 10 to the minus 15 molar. And that's exactly what this is telling us. It's 10 to the minus POH, or 10 to the minus 15. Well, this is very, very acidic. So that's A. Now we have the 12 molar. So what I do is take 1 times 10 to the minus 14 divided by 12. And this would be 8.33 times 10 to the minus 16 molar. For the pH, I'd just take, you would do 12, take the negative log of that. So this is 1.08, so again, a negative. And then for this one, so we want, this is going to have to be 15.08. Add these up, 14, 14, 14. Multiply these together, 1 times 10 to the minus 14, 1 times 10 to the minus 14, 1 times 10 to the minus 14. And this is again acidic. I mean, all of these acidic. Okay. Now, how about this guy here? 7.83 times 10 to the minus 7 molar OH minus times 1. Okay. And I come up with 3, 6, 8. So it's 1.30 times 10 to the minus 8 molar H3O plus. Let me double check that. And as a check, just get done, multiply the two answers that you have, and I get, well, about 1 times 10 to the minus, it looks like when I rounded that I went off a little bit, but it's 1 times 10 to the minus 14, good. And then I take that, 1.3 times 10 to the minus 8 log, so it would be 7.89 here, and then I'd subtract that from 14 to get our answer here, 6.11. So this is slightly basic, and I just want to do one check here because I'm not quite sure of that one number. I want to just see how much I rounded there. Oh, I see. Okay. Times. This actually is better to call it 1.28. My calculator ran out of space, so it rounded for me. This is closer to the truth. So that makes more sense. So you'd be given a table, fill it in, all the species. That's the best way to do it, I found, and that's most likely what you're going to see on my exam.